Good morning, my dear students. Good morning. Nice to meet you all today. Okay. Okay. I think camera is all right. No, right. Right. It's okay. I will handle today class. So just a few minutes. I will handle today class for you. Where is that one? Is it all right now? Good. Right. So I will share today notes. Right. Yeah. And I will discuss. Today we are going to see very interesting thing. Okay. Element stiffness matrix for a arbitrarily oriented truss element in space. Right. It is a three-dimensional. That is, I have a line element, axial element. That is called line element, axial element. Okay. But I am keeping it in space. It means three-dimensional. I have x, y, z Cartesian coordinates. There I am arbitrarily orienting somewhere that axial element. Okay. Now it is called a truss element in space. Okay. That is element stiffness matrix for a arbitrarily oriented truss element in space. That is the meaning of it. Okay. So it's a three-dimensional. First, let us discuss in three-dimensional. Later we will change that into two-dimensional because mostly we will be dealing with the analysis of plane truss. For the analysis of plane truss, the truss, all the members are going to lie in one plane. No. So we require only x and y coordinates, right? In the Cartesian coordinate, we don't require z. But in space truss, z coordinate is also there. Okay. First, I will discuss how to develop element stiffness matrix for a truss element, that is axial element, line element in space. Then we will change from that how to get element stiffness matrix for a plane truss element. That we will see later. Okay. Simplification we can do it. That required simplification we can do it later. Right. That's conversion. Okay, we will do it. Right. A typical truss element arbitrarily oriented space is shown in figure. Right. So I have a truss element which is arbitrarily oriented. Just imagine this is the corner of your room. Okay. Just imagine what is shown here is a corner of your room. Right. One corner is x-axis, then y-axis. And positive z-axis is here. How? You have to take a right-handed threaded screw, keep it here, and turn it from x to y. The direction in which the screw moves represents the positive z direction. Okay, so I have chosen a positive set of Cartesian coordinates. Just imagine, just visualize this way. In a corner of your room, in a room you have a truss member oriented like this. This is the corner of the room. Just imagine, okay, your x, y, z axis are the corner of the room. Now, whose coordinates? Say this is ith joint, this is jth joint, okay, in the truss element. Here, its coordinates is x1, xi, yi, zi, okay. So I have shown here its projection. I projected, okay, and then shown here. What is mean by x-axis? It means the point is at a distance xi distance from this z-axis because the x direction is measured in x direction. No, the x direction it is at a xi distance. The y direction, this point is at a yi distance. Okay, in the z direction, the point is at a zi distance. Okay, located. Its coordinates are xi, yi, and zi. You know. Similarly, the coordinates of jth joint is xj. I shown that also xj, yj, and zj. Its projection I shown. Okay, it's projected this way. That is the meaning. The coordinates. Hope you can visualize this picture. Okay, visualize it in three-dimensional. Then only you can able to understand. Okay, that is 3D. Okay, in 3D you just three-dimensional you imagine xj, yj, zj. Its coordinates. Okay, and whose degrees of freedom, nodal degrees of freedom, or in x direction yi, in y direction va, in z direction wi. Okay. Similarly, the jth node, nodal degrees of freedom in x direction uj, in y direction vj, in z direction wj. Okay. Likewise, we are considering arbitrarily oriented truss element. Okay. Now, please all of you listen. In engineering mechanics, actually in our institute we don't teach that much. There's a subject engineering mechanics you have studied in your first year. In many reputed institutions like NIT and IITs, they teach in the engineering mechanics analysis of trusses in the statics. Okay, in statics they teach to explain the concept, the conditions of equilibrium. The best thing is to teach analysis of trusses. Okay, there are several methods followed: method of joints, method of sections, method of members, and tension coefficient method. There is another method called tension coefficient method. to analyze not only trusses, even frames can be analyzed. Okay, simple frames can be analyzed using the tension coefficient method. There, I used to teach in REC Warangal during when I was working as a lecturer at REC Warangal. I used to teach for first year student in engineering mechanics all this method. Okay, method of joints, method of sections, method of members, tension coefficient method also. There we used to get that use that direction cosines. Okay, whether you heard of direction cosines or not, I don't know. Probably you must have heard it in your mathematics. Okay, direction cosines, or in matrix method of structural analysis also you must have come across the term direction cosines. Okay, the direction cosines of the elements are given by direction cosine means nothing but it is the angle. You take the angle between, because the truss is arbitrarily oriented, no. So the angle between the truss and x-axis, okay, that angle you take. Cos of that angle is called direction cosine with respect to x-axis. Okay, what is the angle made by this truss member with y-axis? Okay, you take that angle, and cos of that angle is the direction cosine of that truss member with respect to y-axis, and direction cosine of the arbitrarily oriented truss member with respect to z-axis means you have to measure the angle between z-axis and the arbitrarily oriented truss element, and the cos of whose value is this one. Okay, how do we get it? From the coordinates. We have these Cartesian coordinates. Okay, the Cartesian coordinates of each node is known. Ith node and jth node are known to us. From that, how do we get, say the length of the element is capital L. Okay, how do we get the direction cosine? So please see here, to represent direction cosine, we are using the notation C L or C suffix x. You will be comfortable if you use LMN. Okay, direction cosine. L means with respect to x. Direction cosine with respect to x, direction cosine with respect to y axis, direction cosine with respect to z axis n. Okay, LMN is the easiest way of remembering. But however, since for finite element method you are following Krishna Raju book, Professor C.S. Professor C.S. Krishnamurthy textbook, right? He adopted in his textbook this notation: C suffix x, cosine, no, direction cosine, C, cosine. So C he used C suffix x, C suffix y, C suffix z to represent direction cosines of a arbitrarily oriented truss member with respect to x, y, z axis. Okay, he used this kind of notation. I also want to use the same thing, Cx, Cy, Cy, Z to represent direction cosines. It may be noted, you can use Cx, some textbooks they have used LMN to represent direction cosines. You most probably you will be comfortable with LMN. Later you can change that one to LMN. Okay, now you will proceed with the Cx, Cy, Cz. What is Cx is equal to, what is the projection of this member on x-axis? You project this member on x-axis, what is its length? Which is xj minus xi. If we know coordinate, no, xj is known. It means its distance from, actually its location from along x-axis is known. Okay, and this node, whose location from along x-axis is known, xi. Xj minus xi will give you the projection of this member, okay, on x-axis. Otherwise, this side, just you treat its projection. Actually, this truss member is arbitrarily oriented. Just imagine in the plane of the monitor. Its projection is on the plane of the monitor. Okay. Now this is, please see here, xj minus xi. Xj minus xi will give you this distance. Okay. I want cos of the angle between the member, inclined member, the truss member, and the x-axis. Okay. So this is the cos of this one. Cos of this one is what? Adjacent side divided by hypotenuse. What are adjacent side here? So I want direction cosine cos theta here. The cos theta here is adjacent side divided by hypotenuse. Adjacent side is xj minus xi. This is distance. Okay, xj minus xi divided by hypotenuse, length of the truss member. So L. So this will give me the direction cosine. Once I know the Cartesian coordinates, the coordinates of the ith node and jth node, I can get the direction cosine of that member with respect to x-axis this way. Similarly, the direction cosine with respect to y-axis, Cy is equal to yj minus yi. Okay, yj minus yi. Okay, how? Let us see. See here, this is vertical is y-axis. No, I want just this truss member is inclined some manner. Just project it on the plane of the monitor. Okay. Now, see, you just consider a right angle triangle here. You consider a right triangle triangle here. I want the cos of the angle between the inclined member, truss member and the y-axis. This is cos of this. Cos of this theta is equal to this adjacent side, this side, okay, divided by hypotenuse, length of the member. What is this projection? This side is nothing but this side, okay, yj minus yi. You see, in this right triangle, this is yj minus yi, this distance, which is nothing but this distance, okay. So cos of this theta is yj minus yi divided by L, hypotenuse. Adjacent side divided by hypotenuse, okay. In this right triangle, I am getting adjacent side, okay. So that's why, thus I am getting the direction cosine with respect to y-axis. Next is Cz. Similarly, Cz also can be shown. You have to visualize, imagine, okay. Zj minus Zi divided by L, okay. I hope you will understand. Apply your mind and think and visualize, imagine what is the angle made by this member with respect to x-axis, y-axis, z-axis, and cos of whose value. How do we get it from the Cartesian coordinates, the coordinates of the ith and jth node and all? Mathematics. I hope you will understand. You have to refer this figure and apply your mind and understand. However, I have explained somehow. Okay, not bad. I have explained the required explanation I have given. But sit and think and apply your mind and understand. Okay, this way we are getting where xi, yij, zi and xj, yj, zj are the coordinates of the nodes I and j respectively. Cartesian coordinates of the nodes respectively. Okay, very good. The length of the member. If you know the coordinates, this length of the member also can be programmed in the computer software. Okay, what is the length of the member? How do you get xj minus xi whole square plus yj minus yi whole square plus zj minus zj whole square, whole root? Okay, this you know, you are aware because this explanation already you are mathematics you have studied, you are aware of this. Okay, now L can be obtained this way from the coordinates of the ith and jth node. Right? This is your fundamental mathematics. You know, aware of this. Okay. The variation of displacement along the member direction R is given by, now please see here, the variation of the displacement along the member direction R is given by, please see here, this is along the member direction, take it as R. Okay. Along the member direction, take it as R. The variation of displacement along this member is given by, see here, I have given u suffix r is equal to, I will give you explanation later. U suffix r means variation of displacement along the member, somewhere, anywhere on the member, the variation of displacement equal to the difference, okay. That is Li uiir plus Lj ujr. It means Li, okay, right, length of the member, right. Li I have written, no problem. Length of the member. Uir means the ith node displacement in the R direction, the member direction. Ujr means jth node displacement in the member direction or rj direction. Okay, that's what. This into length, this into length. You have to sum up algebraically. You have to sum up. Okay, you may not understand here. Let us see here. I have written something. Let us see. What is that? I have written something. What is that? Let us see. Okay, view. No. Rotate. I will rotate and show you. Okay, rotate. Shall I do clockwise? Is it? Yeah, it's here. Change in length equal to. Please see here. UJR means jth node. So please see here. You have jth node, ith node. What is the change in displacement? Deformation. What is the displacement in jth node in the member direction or direction? That minus ith node, okay, displacement in the R direction of the ith node. The difference will give you the change in length. That divided by original length L will give you the strain in the member. Okay. So now I want to obtain the strain in the member. First I am writing the change in length is equal to yjr minus yir. Can you able to understand? Yjr means displacement of jth node in R direction, the member direction, minus uir means displacement of deformation, or the displacement of ith node in the R direction. The difference in displacement will give you the change in length of the member. That would be the length of the member will be giving the strain in the member. Okay, let us see. That is equal to, I have written using the direction cosine here. So using the direction cosine, Cx uj, this is u, Cx uj plus Cy vj plus Cz wj. It means I want R direction, okay? The first jth node, take jth node. I want its displacement in the in its own direction, R direction, say, right? That can be obtained by resolving. In the x direction, we know displacement, which is uj. In the y direction, we know the displacement of the jth node, which is vj. In the z direction, we know the displacement of the jth node, which is wj. Now you resolve this displacement in the r direction, in the truss member direction. How do you get it? Resolving, no, cos theta, isn't it? Cos theta is direction cosine. So uj means the jth node displacement in what is that? What is I written? uj, x direction. Displacement of jth node in x direction is uj. That into direction cosine cos that is cos theta, that is cx. Okay, cx will give me its resolution along r direction. I am resolving the displacement in r direction. Similarly, I am resolving the displacement in y direction along r direction. That is cy vj plus cz wj. This will the sum will give me the final displacement of jth node in its own direction, r direction. Okay, because the nodal degrees of freedom I have in the x, y, z direction. If I want to resolve it, cos theta, that displacement, cos of the angle between x direction and the member direction. Okay, so that is nothing but direction cosine. So cx uj plus cy vj plus cz wj gives me the sum gives me the final displacement of rth node in r direction. That minus this uir. Okay, uir means ith node, come to ith node. Similarly, resolve the displacement in x, y, z direction along the member direction r. Resolve it. That is using direction cosine. Instead of cos theta, we are substituting cos theta is nothing but direction cosine. Okay, cx ui plus cy vi plus cz wi. I have resolved all the x, y, z displacements in the member direction, r direction. Okay, now I got the this way I am getting the change in length of the member. What is the change in length of the member? It can be obtained this way. Okay, I will come. Okay, yeah. Now we have come to that one. This way we are getting this one. I have written. Forget about this. It's not clear. There I have shown something. Okay. So please see here. This UR I will rewrite later. For a three-dimensional truss element, it can be shown that UIR, why we are getting minus sign. If you take this minus sign inside, all become minus no. So that's why I have written here. Minus CX UI minus CY VY VI minus CZ W. It's not necessary. Okay. Similarly, UJR is equal to CX UJ, this one, the first term. I have written this one. Okay. This I have written. Not necessary. If you write this way, the more than sufficient. Again, you need not reread this. Okay. So I leave it. Where UI, VI, WI, UJ, VJ, and WJ are the displacements in global direction at nodes IJ respectively. Okay. The axial strain epsilon r along the member axis r. Now I am coming to the axial element. Okay. Now we are coming to the important one. The axial strain epsilon r. Okay. Now I want to get the strain in the member. We call it as axial strain. The axial strain epsilon suffix r. R means r direction is member direction. Okay, along the member direction, right? Epsilon r along the member axis, along the member direction or along the member axis, or along the member axis r of the element is, I told you, change in length divided by L, isn't it? Change in length divided by L. Epsilon r is equal to the change in length we obtained just now. Okay, that I have written here. Cx uj plus cy vj plus cz wj minus okay, within bracket cx ui minus I taken inside minus cx ui minus cy vi minus cz wi. I have taken inside. Okay, divided by L. This is the strain. Therefore, that is equal to, I have written this in the matrix form, 1 by L into minus Cx. It's not continuous. These are coefficient matrix. I have written a matrix here. Please remember. Okay, this one is written in the matrix form. This equation is written. This strain, axial strain, is written in the matrix form like this. The coefficient minus Cx minus Cy minus Cz, Cx Cy Cz plus, okay, into Ui Vi Wi Uj Vj Wj. Why this ui, vi, wi and all minus cx, minus cy, minus cz. That I have written first. That's why I have written ui, vi, wi. Okay. If I multiply, I will get minus cx ui, minus cy vi, minus cz wi. This terms I will be getting. Okay. Again plus cx, cy, cz I have written, and uj, wj, sorry, uj, vj, wj I have written. So if you multiply cx uj plus cx uj plus cy vj plus cz wj, I will be getting these terms. I will be getting. Okay, this equation only, this strain, the axial strain in the axis of the member R is written this way in the matrix form. Okay, thus the strain displacement matrix B can be written as, okay, now please see here. Now this relates strain in the element with null degrees of freedom. This is null degrees of freedom. Okay, which matrix relates the strain in the element with null degrees of freedom? We know the matrix which relates null degrees of freedom and strain in the element is nothing but strain displacement matrix. Already I told you. Okay, already we have discussed. The matrix which relates null degrees of freedom and variation displacement within the element is shape function. The matrix which relates null degrees of freedom and strain in the element is called strain displacement matrix. Okay, thus the strain displacement matrix B can be written as this one, 1 by L into this one. I have written B equal to 1 by L into minus Cx minus Cy minus Cz, Cx, Cy, Cz. It may be noted, please see here, since this notation is used in the CS Krishnamurthy book, I am using it. If you don't like, you can use minus L, minus M, minus N, plus L, plus M, plus N. LMN also you can use to represent direction cosines. Okay, that we will use it at the end. Let us discuss with this notation, because that is the main textbook you will be referring. That's why. Okay, the axial stress in the element is, now I am coming to the axial element. Just some simple discussion in between. The axial stress in the element, how do you get? Sigma equal to Young's modulus. Okay, constitutive matrix, Young's modulus into B into D. This is because it's strain. No, this is axial strain. Axial strain into Young's modulus will give you the stress in the element. Okay, that's what. This way we can obtain. Okay, du. This is d sub u. Okay, B into du. Right. Not necessary. It's okay. The stiffness matrix. Now we are coming to the important part. This you can omit. This is not necessary. Just a discussion in between. How do you obtain axial stress? Just a discussion. Okay. Because you have to tell somewhere. How do you, once you know the strain, how do you get it? Okay. Now I am coming to the important part of the discussion. The element stiffness matrix, you can write even element here. The element stiffness matrix K for a prismatic element can be evaluated as, now I am writing. So the element stiffness matrix for this arbitrarily ordered truss element K equal to triple integral, okay, constitutive matrix C, okay, which is nothing but it's axial element, one dimensional. It means one dimensional means in the direction of the element, R direction. The R direction is one dimensional, okay. So constitutive constant is only Young's modulus, E alone. So E divided by L. Why L? Why L square? Because B matrix is equal to 1 by L. And then B transpose I want. There also the another 1 by L varum. Okay, that because B transpose into constitutive matrix C into again B matrix, no, state displacement matrix. So twice I will be getting 1 by L. Only the transpose matrix, this will be written in the vertical direction. That's all. Instead of row, we will be writing in column. Okay, the transpose of it. That's why E by L square into the B transpose. The strain displacement matrix transpose is written here. Minus Cx, C, minus Cy, minus Cz, Cx, Cy, Cz into the B matrix. Minus Cx, minus Cy, minus Cz, Cx, Cy, Cz. Plus, okay, into dV. Right? That is equal to this dV is, I have forgotten to write here. This dV equal to A into dx. Okay. So area into dx. You can write it as AE by L. Okay. So AE by L into, right? Now you multiply. This way you can memorize this elements, this stiffness matrix. Please see here. Only thing is you have to write this B transpose. This into this will give you the matrix. Cx into Cx. What is that? Cx square. Cx into minus Cx into minus Cy plus Cx Cy. Okay. Next minus Cx into minus Cz. Okay. Minus Cx Cz. Next minus Cx into plus Cx. So minus Cx square. Cx minus Cx into plus Cy minus Cy Cx Cy. You can write this order also, minus Cx Cy. Okay, minus Cx by Cz. Likewise, you have to take, you know how to multiply these two one. Okay, next minus Cy into minus Cx, so plus Cx Cy. Next minus Cy into minus Cy, so plus Cy square, minus Cy into minus Cz, so plus Cy Cz. Okay, minus Cy into, likewise you have to multiply in order to get this matrix. Hope you will you can understand. Okay, you will be getting it's 6 by 6 matrix you will be getting. This is nothing but the element stiffness matrix for this arbitrarily oriented truss element. It's cut to know. I will show it here. Yeah, this way you can get it. This element stiffness matrix. That's all. This is the element stiffness matrix for truss in space. Okay, the truss element in space, right? How do you remember, sir, this one? You did not memorize. Don't memorize. This alone you remember. A by L into, how do you obtain this? You have to write this one. Minus Cx, Cy, Cz, minus Cx, minus Cy, minus Cz, Cx, Cy, Cz, you write it somewhere. Roughly you can compute. Minus Cx, minus Cy, write it in the row form, write it this in column form, and multiply these two in order to get this 6 by 6 matrix. You need not memorize it. To obtain it, please, doing exam, you can do multiply these two matrix like this. You can write it and multiply and write down. Okay, A by L. While solving problem, this derivation is asked now, you have to do fully. Okay, develop the elements stiffness matrix for a arbitrarily oriented truss element. You have to do it fully, whatever I have discussed. While working problem, if you want, in case, just I am telling, space stress you will not get, only some space stress you will not get, only you may get only some plane stress only. Okay, suppose in case you in the field practical, you want to analyze a space stress. If you want to write element stiffness matrix for each member, now how to write A by L into this only, you have to memorize. This is the element stiffness matrix for a truss element in space. Remember. Okay, from this I want to get a truss element in a plane. How do I get? For that, please see here. From this, omitting the terms contains Z. Stiffness matrix for plane element can be written. That's all. You have to omit the terms which contains Z, because once it's a space stress, plane stress means no Z axis, isn't it? Only X and Y is Y axis. So whatever term that direction question of Z you neglect, right? So only you take Cx square, Cx Cy. This is not there. This will be 0. Cz Zx will be 0. Again, okay, 1, 2, and the third term will be minus Cx square, and then minus Cy Cx. This Cz Cx will not be there. This will be 0. Okay, wherever Z is there, that direction cosine for Z is there, C suffix Z is there, omit that term. You will be getting a 4 by 4 matrix. Okay, for a plane truss. Okay, so it may be noted Cx. If you don't later, you can, if you want to write, you can write, instead of Cx you can write L. So Cy you can write M, instead of Cz you can write N. Okay, if you want, that's a problem. I will show you how do you get a element stiffness matrix for a plane truss. A truss element lying in a plane. See here, I have shown. See here, K equal to A by L. This is the element stiffness matrix for a plane truss. Please see here, element stiffness matrix for a plane truss. Instead of Cx, Cy, Z, I have written Lmn. Okay, A by L, L square, Lm minus L square minus Lm. Okay, which is nothing but Cx square. What is this? Cx. What is Cy? Cx Cy. Okay, minus Cx square minus Cx Cy. Okay, that's what I written this manner, Lmn manner. Okay, this is element stiffness matrix. How do you get it for a plane truss? Is it necessary to memorize? No need. How do you take it? Here you neglect Z. Here you neglect Z. Cz you neglect. Only you will be getting Cx Cy. Neglect minus Cz. Neglect this one. Only you will be getting minus Cx minus Cy minus plus Cx plus Cy minus Cx minus Cy plus Cx plus Cy. Okay, okay, multiply. You will be getting element stiffness matrix for a plane truss. Easily you can do it. Okay, definitely you will be getting problem on analysis of plane truss. There you have to write this element stiffness matrix. Okay, this you need not memorize. you can obtain. How do you obtain? Write in column, okay, L, M, minus L, minus M, and then LM, okay, like this. No? Minus L, minus M, and LM. Here you write minus L, minus M, LM. Okay, L and M, afterwards M, okay. Multiply, 4 by 4 matrix. Okay, multiply. You will be getting, hope you will remember. See here, in the row I have minus L, minus M, L, M. This side I am getting that strain displacement matrix, no? Minus L, minus M, L, M. Multiply minus L into minus L, L square. And then minus L into minus M, LM. You can do it. Okay. This way you can multiply and write down this. You need not memorize. Don't memorize it. You can obtain it by multiplying those two. You have to apply your mind and understand the concept. Okay. I have done it for plane truss. See here. I have done it for plane truss. If it is, space truss, arbitrary oriented truss element in space. If you want it for a plane truss, you have to omit this z axis. That's all. Only x, y alone lying in a plane. Okay. Accordingly, you have to write direction question cx, cy alone. And you can derive it also. For plane truss also, you can develop. From this derivation, you can do it. Apply your mind. Think over and do it for a plane truss. Or you can do it for a space truss. Finally, you can reduce. Okay. Reduce that to a plane truss like this. Okay. From this, omitting the term containing z. Okay. Hope you will understand. This way you got adopted. Hereafter, there are some problems. The derivation, development of element stiffness matrix for truss element in space as well as truss element in a plane. Both are over. Okay. Development of derivation of element stiffness matrix for arbitrary oriented truss element in space. That is truss element in space. And then a plane truss element, space truss element and plane truss element. Truss element lying in a plane. Okay. Plane truss element. How to develop element stiffness matrix? I have shown it here. Okay, this is for 6 by 6 matrix for AE by L into 6 by 6 matrix for a space truss element. Okay, and AE by L into 4 by 4 matrix for a plane truss element. Okay, notation finally you can convert into LMN because you will be comfortable, right? You can multiply. Even you can write CX, CY also, no problem. Okay, as given in CS Krishnamurthy book also, you can do it. To obtain it, you have to multiply these two. To obtain for plane truss, only you have to multiply. Omitting the Z, you have to multiply. Hope you can understand. Okay, you'll be getting 4 by 4 matrix for a plane truss. For a space truss, you'll be getting 6 by 6 matrix. Other procedures, things are same. Okay, instead of DV, you'll be getting DA for space truss. That also you keep it in mind. Okay, that's all. Hereafter, there are some problem which are incomplete. I have not done fully this problem. I will be telling how to do it. Okay, you have to do it. I have just left incomplete in between. The problems and all I have not done. Next class I will do them. Okay, just I will tell you the procedure of doing it. Right, just for your practice. Moreover, the notes is written long back in a rough manner. I have not. I just scanned it. Okay, I don't prefer to write once again the notes. This problem, take it and solving. So whatever notes I have, more than sufficient. Okay, please. I will be telling the next class how to solve it. Okay, you will be solving in your class notes, right? With this, I will stop because today I told you how to develop element stiffness matrix for a arbitrarily oriented truss element in space, and then from that, how do you obtain the element stiffness matrix for a truss element lying in a plane? That is plane truss element. Okay. Hope you will understand. Okay. You practice it. Next class I will continue. With this, I will stop today class. Right? Is it okay? Problem I will do in the next class. Okay. Next class I will do the problem. Just hope again explaining. I don't want to confuse you. Apply your mind. Okay. Listen to my video. Apply your mind, you will understand. Just I want to record your names. Okay, you all are attending. Very good. All 24 of you are attending. Full attendance is there. Always M.Tech students are very sincere students, right? Very good. So I am so happy to see all of you are attending because you all 24 of you are attending. You are sincerely attending class. Very good, right? I will first stop recording, right? Then we will discuss anything. Thank you. Bye, 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 bye. To see you. If you want to discuss anything, we will discuss.